The first part is this phenomenon of concentration of measure. So let me write it down. So the missing part last time, concentration of measure in a hypercube. So what it means is that we have this hypercube. This is the picture. Up here is the whole set n. Down here is the empty set, right? And each layer, so for example, this K is, this layer K means all subsets of size K. And the concentration measure is saying that, of course, the total size trivially is 2 to the n. There are 2 to the n subset of n. Concentration of measure is saying that most of the weight, most of the measure is concentrated around the middle layers. The top and bottom, 99% of them, they are negligible in terms of size. Here is the precise statement. So most weight of the cube, the hypercube, is around mid layers. Okay. Here's the corollary. Here's the lemma or proposition, maybe. For any epsilon bigger than 0, and then we have the sum of n choose k. K goes from the bottom, 0 is the empty set, all the way to, let's say, 1/2 minus epsilon n. So just right below the mid layer, epsilon n distance, this is negligible. Okay, actually exponentially small. This is at most, let me divide it by 2 to the n. Divide by 2 to the n is at most e to the negative epsilon squared n, exponentially small. All right. So to prove this, let's start out with proving the type of Chernoff, one basic type of Chernoff type concentration inequality using Markov inequality. So recall Markov. Markov inequality is saying that for any random variable x, non-negative, okay, we have that it doesn't have to be integer valued. We gave a proof for integer valued non-negative random variable x last time. I'll leave it as exercise for you to prove for just real valued. So we have that the probability that x is bigger than some number t is at most the expectation of it divided by t. Okay, this is Markov inequality. We're going to prove the following Chernoff type concentration inequality. If which bounds okay, so we have x1 to xn independent random variables. We have x1, xn independent random variables, which is centraled, meaning that they have mean 0 with mean 0, expectation 0, and taking value in -1 to 1. So each one of them in absolute value is at most 1. Now we're going to let x to be the sum of xi. We want to bound the probability that x is large. Okay. For a moment, let's suppose this is the simplest case that xi are Bernoulli random variable, meaning it takes 1 with probably 1/2, takes -1 with probably 1/2. Then, oh, okay, let's forget about that. We know each xi has mean 0, right? So the mean of x by linearity of expectation is 0 as well. So we want to show that x is highly concentrated around its mean 0. So we want to show that this probability is small. It's actually it has an exponential tail. The probability that x is at least epsilon n deviate away, epsilon away from mean is exponentially small in terms of n. So we have epsilon square n over 4, say. Idea. The idea is basically we're going to apply Markov inequality to exponential moment of this random variable. Okay. Apply Markov inequality to the exponential moment. The exponential moment is this guy, e to the lambda x, the expectation. Okay, so let's do that. The idea is simple. Proof. Let's write out this exponential moment. We have for this exponential moment, x is sum of xi, so let's write it out. We have lambda sum of xi, I goes from 1 to n. Now, the sum in the exponent is product. So this equals to expectation product I from 1 to n, e to the lambda xi, no problem. Expectation of product of random variable, now we use independence of xi. Independence means we can move expectation inside, right? So now, because of the independence, we have this equals to product 1 to n expectation of e to the lambda xi. Now let's look at how each term behave. Look at how this behave. Let's first use the Taylor expansion to expand this single term. We have, because let's expand it. For each term, expected value of this guy equals to 1 plus lambda times exi plus lambda square over 2 factorial expectation xi square plus lambda cube over 3 factorial expanded out dot 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 dot. Okay. What do we know? We know xi has mean 0, so this guy is 0. Mean 0, right? So we have this term. So let's assume lambda is at most 1 for now. We should take lambda at most 1. Then if lambda is at most 1, we also have, since xi in absolute value is at most 1, it takes value between -1 and 1, we have This guy is at most. Now let's continue. This is the reasoning. Continue from here. This is at most 1 plus lambda square over lambda cube over 3 factorial, dot, dot, dot. Okay. Which is at most e to the lambda square. Okay. This is true. So we get right. So this is for each term. Each term is at most e to the lambda square. We have n terms. So altogether, we have this exponential moment is at most. So we have exponential moment of x is at most e to the lambda square times n terms. Now we apply Markov inequality. So the probability, now Markov implies probability, the bad event we want to bound is x deviate away from mean by epsilon n. So probability that x is at least epsilon n is at most the expectation of, okay, first let's write it in this little trick. Exponentiate the thing inside. So this is the same as saying probability of e to the lambda x is at least e to the lambda epsilon n. This is the same thing, right? Now we apply Markov. Maybe I should do this. Okay, so this is at most by Markov expectation of this guy, which is just the exponential moment, divided by this deviation. So we have e to the lambda epsilon n, which is at most e to the lambda square n minus lambda epsilon n. Okay. Now you just choose optimal lambda. We can choose lambda. You can take the derivative, and we will see that take lambda to be epsilon over 2, we will get the desired result. This is at most e to the negative epsilon square n over 4. Any question? Okay. Now let's prove this concentration of measure, proposition 1. Okay. We want to prove that up until epsilon n from the mid layer, all the bottom one, they are exponentially small compared to the whole measure. So let me copy this maybe. Okay, so we want to prove these. Proof, we use concentration measure. We use this Chernoff type bound. So we're gonna take Bernoulli random variable x1 to xi, xn. Bernoulli random variable. It means it takes value 1 and minus 1 with probability 1/2, equal probability. Okay. Then of course it has mean 0, each one of them, and we are taking independent. I forgot to say independent Bernoulli random variable. So we have the independence, we have mean 0, we have the absolute value is bounded by at most 1. So everything is satisfied. Let x to be the sum of xi, 1 to n. Then we have the above theorem that x is less than, by symmetry, everything is symmetric, right? Less than how to say, by symmetry, one can also show x less than epsilon n is the same thing. What you can do is you can replace xi by negative xi. You'll get this symmetry. Okay, so we're going to use this for minus 2 epsilon n. This is at most e to the negative epsilon n squared n. We have this. Now let's look at what this is. What does this event means? Okay. Cool. So we have n items. Each item is 1 with probably 1/2. So if you consider k to be the number of plus ones in xi, then what is x? X equals to k plus k times 1 plus m minus k. K of them is 1, then m minus k of them is negative 1 times negative 1, right? Which is 2k minus n. Okay, so these events being x being at most negative 2 epsilon n is equivalent to this event is equivalent to k is at most n over 2 minus epsilon n, right? So this is the same as saying among n items, the probability that at most n½ minus epsilon n of them is plus 1. You can associate these as taking a subset of n. And each subset is chosen with, so each outcome of xi, you can associate to subsets one-to-one correspondent to n, right? So this event is the same as a uniform random subset of n has size at most n over 2 minus epsilon n. Okay? And this probability, we can write it. This probability of this event is exactly, we have 2 to the n total number of subsets, uniform random chosen, right? And those that at most n over 2 minus epsilon n is precisely the previous layers. And that's it. We have this guy. Oh, what did I do? This guy is the same as this guy. Okay? Which is at most that. That's it. Any question? Okay. That finishes the missing part last time. Right. So let's move on to more applications of first moment. So we're going to see some geometric applications. Okay. We're going to see Familiarity trotter. while crossing. Okay, so let's explain things one by one. Let's first explain what is crossing. So in graphs, there's a type of graphs they call planar graphs. That means you can draw them on the plane without any edges crossing each other. Okay. So let's formally define crossing. Hmm. So definition. For a graph G, the crossing number of it, the crossing number of a graph G is the minimum number is the minimum number of crossings in any drawing of G in the plane R2. Okay. So for example, planar graph means those can be drawn on the plane without crossing, has crossing number 0. Okay, here's a simple example. The minimal some example, non-planar example. So the crossing number of, let's say, K5 is bigger than 0. Crossing number of K33, there's no way of drawing them without crossing. These are the simple example. This is K5 and K33. Okay, so K5 is the smallest clique that necessarily will have crossings, no matter how you draw it. And K33 is the smallest bipartite graph that necessarily has crossings. So here's an even easier, another simple example, K4. If you draw K4 in standard way that we're familiar with, this has crossing 1, right? But so that means this is it's not a good drawing this way. There's a crossing here. And a more clever way to draw it is draw it like this. This is again the K4. Number of crossings is 0. Okay. Let's first prove some simple things, recall some simple things. If we have a planar graph, we call these faces of a planar graph in a planar drawing. So this is a face. It has 4 faces here, right? Number of faces equals to 4. And number of vertices equals to 4. Number of edges equals to what? 6. So actually, there's a famous Euler's formula for planar graph. That's for any planar graph G, we have, what is it? E plus, I don't remember. V minus E plus F equals to 2. This is the number of vertices minus number of edges plus number of faces. So here, for example, in this example, K4, we have number of vertices minus number of edges plus the number of faces equals to 2. Good. Sanity check. So far, so good. Any question? Now, the first thing we're going to prove is we can prove a simple upper bound or some relation between number of faces and number of edges. So I will call this a proposition. We have for any planar graph, the number of edges is at least 3 times the number of faces divided by 2. Okay, first of all, this is tight. For example, consider a triangle. It has 2 faces. Inside the triangle, outside of triangle, right? Inside, outside. Number of edges is 3. So this is tight. Exercise, find infinite family of tight example. I don't think this exercise is not very interesting. So we just remark that this is optimal. For example, consider triangle. Proof of this is simple, double counting. How do we do double counting? Let's look at how edges and it's the faces that contains an edge, the relation, okay? So let's double count. So construct the auxiliary bipartite graph. Here are all the faces. Here are all the edges of G, right? And you made a face. A face is adjacent to an edge if it's a part of it, a part of that face, okay? So for example, this edge is adjacent to this face, adjacent to the outer face, okay? This is the adjacency. Okay. If E is not good, I use E for the number of edges. So what symbol do I have? If the edge is a part of the face. A part of the face. Okay. Now, each edge is involved in exactly 2 faces, right? Or at most 2 faces. I feel like say exactly. At most is enough. At most is for sure true. Can the face involved in only one? Can an edge involving only one? Oh, it's possible. It's possible. If your graph is a single edge, there's only one face. Okay. So this edge is incident to just one face. But normally it's incident to 2 faces. Here, 2, right? Here, 2. Here, oops, here, 2. Here, 2. So note that each edge in at most 2 faces. So that means the degree here is at most 2. And note that each face has at least 3 edges. This is simply because each face is a cycle, right? And the cycle has length at least 3. So here, mean degree here is at least 3. Double counting, we have double count the number of edges. Let me call this graph gamma. Double counting E gamma, we get that E gamma is at least 3 times the faces, right? And at most 2 times the edges. So we have E is at least 3f over 2. Done. Then we use this, we can prove maximum size of a planar graph. Another theorem. The theorem. We have a planar graph has at most 3n minus 6 edges. So for any n vertex planar graph, G, E of G is at most 3n minus 6. This is also tight. Also tight. Find an example, okay? I'll leave an exercise for you. How do we prove this? Well, just use Euler's formula and this bound on the number of faces and edges proof. So we have Euler's formula, 2 equals to the number of vertices minus the number of edges plus the number of faces. But we know the number of faces is at most 2/3 number of edges. So plug it in. Simplifying this, we get what we want. Okay. Easy peasy. Now, here comes the crossing part. So far, we're dealing with planar graph. Now, for a general graph G, what we want to do is to get the lower bound on the number of crossings, the minimum number of crossings. So we want to lower bound the crossing number of a given graph. Okay. Proposition. Here's the first easy bound for any n vertex graph with m edges. For any m vertex G with m edges, its crossing number is at least m minus 3n minus 6, right? Okay, let me... I don't care for minus 6. Okay, at least m minus 3n. The proof is also very simple. The idea is that by this theorem above, we know that when your number of edges goes above 3n, you must have one crossing, no matter how you draw it, because it cannot be planar. So you pick an edge that will create the crossing. You remove this edge. So the number of edges decrease by 1. Okay? And we pick up one crossing. When you remove this edge, you remove all the crossings caused by this edge. Then you repeat. If it's still above the threshold, 3n, you identify an edge that causes a crossing. There must exist such one. And you remove. And that's it. So let me write it down. By the above theorem, whenever number of edges is bigger than 3n, there exists an edge involved in the crossing. Okay. Keep removing such edges. That's it. This bound looks very simple and easy. It's not performing very well when it's performing well when when the graph is sparse, when m is say linear in n. Okay, so the remark is that this bound is not very good when for dense graph. the bound, no good for dense graphs. Now we're going to do something which is quite beautiful. We're going to do a probabilistic, we're going to do a sampling argument to bootstrap this naive bound, which works really well for dense graph. So first of all, what sort of bound we should anticipate? If for dense graph, let's say in the densest regime when m is quadratic in n. So for example, if m is, say, quadratic, the densest regime, right? So every crossing involves two edges. The number of crossings could be n to the 4, right? You have 4 vertices. It could be that every 4 vertices create a crossing. I mean, in the worst case. So we should anticipate some, but in this case, this only gives how many crossings? N squared, whereas we want n to the 4. This is the theorem we're going to prove. It's a theorem by independently Aitai, Hvatal, Newborn, Samarati, 82, and Layton in 83. They prove that for any m vertex graph, G, with m edges, let's say m is at least 6n, it's sufficiently dense, then the crossing number of G is at least m cubed over some constant, doesn't matter, let's say 100, n squared crossings. Now let's compare this bound with the bound up there. If the graph is dense, now for dense graph, this bound is what? Is n to the 4, right? That's nice. How do we do that? Any questions so far? Okay, no question. Good. How do we do that? The idea is to do sampling idea. So before I say the idea, maybe let me say some intuition why this idea works, right? The idea is sampling to bootstrap the basic bound. So the basic bound, I mean this basic bound. So let's say heart. Okay. What do I mean by that? In this bound, let's see everything here. We have we have the number of crossings. Number of crossings is like this, right? And this is number of edges. This is number of vertices. So number of vertices involved. In a crossing, there are 4 vertices involved. In an edge, there are 2 vertices involved. And the number of vertices, of course, is 1 vertex involved for each vertex. This inequality, the sort of growth rate of each item is different. So if you do the sampling, the decaying rate is different. Then you can make use of this discrepancy on the decaying rate to boost this basic bound. That's the idea. Okay, let me write it down. So number of crossings, number of edges, and number of vertices have a different rate of growth. And oftentimes, when you have different rate of growth, this sampling is useful. We can then use, maybe I say the thing in the wrong order. First, because observe this, then we can use sampling. So let's see the details. Okay. So the sampling is easy. We're just gonna sample induced subgraph of G, meaning we pick each vertex, because here what we cared about is the number of vertices, right? This is where the discrepancy on the order. So we pick each vertex with probability P. Okay. So proof. Pick an induced subgraph H in G with each vertex chosen independently with probability P. So this is a P-random vertex subgraph. Now, we're going to apply this basic bound to H. We should apply this basic bound to H. So let's first estimate in expectation what's the number of crossings, number of edges, and number of vertices in H. So so we have G, vertices, edges, crossings, right? So we want to prove it's a lower bound on the number of crossings. Let's take an optimal drawing, of course. You fix the optimal drawing. Now you do this random sampling. Number of crossings, let's say, is T. Number of edges is M. Number of vertices is N. Then in H, each vertex is retained in expectation. Okay? With probability P. So there are Pm vertices and P square M edges. This is what I mean by different rate of growth, right? Here. So I think in the future, when you see some basic bounds and the items involved have different rate of growth with respect to something, here something is number of vertices, then you can do some sampling. Most likely you will get something better. So here, P square M is the number of edges in expectation. What about number of crossings? Well, each crossing is caused by 2 edges with 4 vertices involved. So we have P to the 4 times T in expectation. Okay. Yeah. So, okay. So the expected number of crossings in H equals to P to the 4. This is equality. On the other hand, this guy is at least by this basic bound, at least number of edges minus 3 times number of vertices, right? So p square m minus 3pn. Now we have this inequality. You see why this is useful now? What we want is a lower bound on t. So p is a small number, right? So when p is small, we can then move p to the 4 to the right-hand side. This is much smaller factor than any one of these factors. So we'll get a better lower bound here. So just do optimizing. I will skip the optimizing part. I will tell you how to choose parameter. We're going to choose p so that you should do the calculation yourself to convince yourself that this choice is the best. Choose p so that this guy is half of this guy. Okay, so p square m equals to 6pn. In this way, we're gonna this means p equals to 6n over m, right? In this way, we have p to the 4t is at least 3pn, right? Which implies some calculation, blah, t is at least 3n over p to the 3. And this, if you can compute, is the bound that we want. Once again, this is the probabilistic part. We use first moment here. Different rate of growth. Then you can try to use sampling to bootstrap some basic bound. Okay, if in the basic bound, the items involved have a different rate of growth. Good. So this is what I want to say about crossings. Let's see some applications of this theorem. This constant doesn't really matter. Just remember that the number of crossings is at least number of edges to the power 3 divided by number of vertices to the power 2. Okay. The first application is similarity trotter. This is the incidence, counting number of incidents of points and lines in the plane. So applications. Incidences. Suppose we have a set of lines. Let me first define incidences. Given a set of lines and a set of points, let's say a set of lines L and a set of points P, okay? An incidence is nothing but there is a point in P and there's a line in L such that this point lies on this line. For such a pair, that's an incidence. It's a pair PL such that P lies in the line L. Okay, and what we want to do is to count, to estimate, to bound the number of incidences for a given set of lines, for a set of lines and a set of points in the plane. Here's the theorem. We want to upper bound the number of incidences. Well, if you have m lines and m points, it's very easy to prove that, well, it's trivial that number of incidents is m times n. But can we improve it? And okay, maybe let me start with some easy thing. The question is, given a set of n lines and m points, how many incidences can there be? Okay, an easy bound, let's try to get an easy bound, is the number of incidents is at most n to the 3/2. Why is this easy? Construct auxiliary graph where here you have lines and here you have points. Actually, let me write points on the left. Okay, and you put an edge if P lies in L. So P adjacent to L in gamma if and only if P is a point on the line. Okay, for this graph, notice that it's C4 free. What does C4 free? If you have a C, simply because every 2 points determines a line. Okay, as every 2 points determines a line and vice versa. Every 2 line determines a point. We cannot have 2 lines intersecting at 2 points. That's what C4 means. C4 free, and you have an n by n vertex C4 free graph. It has an extremal number. And the number of edges is the number of incidents, right? Number of incidences equals to E of gamma, which is at most the extremal number of 2n C4, which is big O of n to the 3/2. Turns out this bound is far from optimal. And there's this classical result of Familiarity and Trotter, who proved that the number of incidences is actually of order at most n to the 4/3. So Familiarity Trotter. Okay. So for any n points and n lines in the plane, the number of incidences is at most 8n plus, oh, wait. Let me just write 10. N to the 4/3. Okay? Actually, there's an asymmetric version. Let me leave as exercise. If we have m lines and m points, you can prove a bound of at most 10 m plus n plus n to the 3, what is it, 2/3, m to the 2/3. Okay, but in the symmetric case, when m equals to n, this is a lower order term. This is leading term, which is order n to the 4/3. So let's just do the symmetric case. The proof is a very clever proof using Whose proof of this? Is it the original proof? This, please check. I'm not sure if this is the original proof. There are several proofs now. The crossing them are proved maybe by someone else, not by them. Check. So what's the idea? It looks at the first glance, it has nothing to do with crossings. Well, we've been talking about crossings, so we're going to use crossing lemma. So how do we make link connection of these two seemingly unrelated problem? This is why this proof is quite beautiful. At the first sight, no relation with one another. So we're going to build an auxiliary graph in which the number of incidences is related to the number of crossings. And then we can use the bound on the crossing number to give bound on the incidences. Proof. The auxiliary graph is a very simple one. Let me first describe it and then write it down in details. Suppose this is our line. Okay. Suppose this is our line. I want to draw in a prettier way. 1 second. Let me try it again. Okay, like this. Now, this is our line and this is our point. Let's say. Lines and points. Our auxiliary graph will have the vertex set, the set of all points as vertices. Okay, so auxiliary graph gamma, where V of gamma is the set of points P. So let's give names. We have set of points is P, set of lines is P, set of lines is L. Okay. All the points are the vertices. What are the edges? Well, the edges, let me describe it. On the line, you look at all the points lying on this line. Then the edges are just these. Okay. So if we list for each line L with vertices along the line, we will this. For each line L, order the vertices along L as X as V1, V2, K, say. So this is like V1, V2, V3. Then the edges is Vi plus 1 for all I in K minus 1. Okay, these are the edges. Let me draw. This is the edges. This is the edges. This is the corresponding auxiliary graph with the red edges. Is that clear, the definition? Any question? All right, it's very simple. We take the points as vertices, and the edges are just along the line between any two consecutive points. We put an edge, i.e., put an edge between every pair of consecutive points on the line. All right, now let's see properties of this auxiliary graph. First of all, what's the number of crossings? So if we let Li let Si be the size number of points on the line Li, right? So this Li is 3. Then the sum of these sizes is precisely the number of incidences, right? This will imply the number of incidences equals to sum of Si for all Li in L. Okay. Let's call this guy S. What we want to do is upper bound this S. Now let's make connection to crossings. When do we have a crossing? Look at this graph. For example, we have two lines here. If there's a crossing, it happens at one of these points, right? So we have no, that's not what I want to say. What I want to say is what's the number of edges of this auxiliary graph? Okay, number of edges, E of gamma. Well, we know that for each line, we have size Si, and the number of edges associated to each line is Si minus 1. 3 points, 2 edges, right? This equals to sum of Si minus 1. This equals to number of crossing minus n, the total number of lines. No problem. So we can now use crossing lemma. Crossing lemma then implies the number of crossings of gamma is at least number of edges cube divided by 100 number of vertices. Well, the number of vertices is just the number of points, which is n. So this is at least equals to S minus n cube over 100 n. Okay. We may assume S is at least 10n, or otherwise we are done. You can use this lower order term. Oh, well, 10n, right? It will be less than this. So may assume S is at least 2n, otherwise done. Then this is at least S over 2 cube over 100n, right? This is S cube over 800n number of crossings. Good. We get a lower bound on the number of crossings. What about the upper bound? The number of crossings, trivially, it involves 2 edges, right? So trivially is the number of edges of gamma, choose 2. So that's the upper bound. And we also have crossing number of gamma is at most E of gamma, choose 2. Every crossing is caused by 2 edges. So this is at most S minus N squared over 2. Okay. Now you put these 2 bound together, I think we are done. So actually, maybe I do the simplification too soon. Wait. Let's see. So we have wait, there should be a square here, right? No one reminds me. There's a square here. So the number of crossings, lower bound from the lemma is at most. Trivially, number of edges, choose 2. So S minus N squared over 2, which is the same as S minus N is at most. Huh? Something is strange. Ah, okay. I know where I made a mistake. Anyone see where I made a mistake? Give you 5 seconds. Where did I make a mistake? Here, right? It's not the auxiliary graph. I mean, we have n lines to begin with. So every crossing is caused by 2 of these lines. So just trivially, n choose 2. I should put cardinality of L choose 2. All right? This is where I made a mistake. All right. Then it's okay. Ugh. So what I did earlier was okay. Move this down. Okay. So we have now this guy is almost this guy, implying S cubed 100n is almost n squared over 2. There's a square here. Uh, 50 and okay, that's it. Any question? Let's review the proof. Basically, you just do this auxiliary graph. For line point arrangement, you build this auxiliary graph where the points are the vertices and the edges are those segments between consecutive points on the line. Then we can associate the number of incidences to number of edges. Okay, incidences is just precisely the number of points, the size of each line, sum them up. We can then double count the crossing. Lower bound comes from crossing lemma. Upper bound comes from trivially every crossing caused by 2 lines. So n choose 2. That's it. Let's see a second application, geometric application of crossing lemma. This unit distance problem. Ah, I forgot to mention this tightness. So how good is this n to the 4/3 remark? n to the 4/3 optimal. What's the construction? Well, let's consider the points. Grid points in 0, 1, 2, r-1 times. Here's a picture. It's a asymmetric grid where this side is roughly n to the 1/3. This side is n to the 2/3. Okay? R by R squared. So roughly n to the 1/3 by n to the 2/3. You take all the grid points. This is the point set. What are the lines? The lines are all the lines satisfying the mass path through one of the points 0, y, where y is at most up to half this point, pass through one of these points. Okay, this is 0, y. And the slope is in the set. Slope is the 1, 2, or r, n to the 1/3. So that means you grow like slowly all the way to you hit the steepest one hits the top right corner. Okay. Okay. Then it's easy to check that the number of points is roughly 2r cubed. Number of lines is r cubed. And each line through r points number of incidences is r to the 4, which is n to the 4/3. This is optimal. Unit distance problem. The unit distance problem, another geometric problem, saying that if we have a set of n points in the plane, then how many pairs of points can be of distance 1 apart? Okay. This question was raised in the 1940s by Erdős. So, question 1946. Erdős asked, we have n points in the plane, given n points in the plane. How many pairs? How many pairs of them are of distance, of unit distance apart? Okay. If you draw this perfect grid, just to get some feeling, we want to maximize the number of pairs, right? Maximum number of pairs that are distance 1 apart. If you draw this perfect root n by root n grid, it has n points, and the number of unit distance pair is roughly 2 plus little o 1 times n. It's easy to check. There's a clever construction using a finer grid. So now, so far, the lower bound is superlinear, is n to the 1 plus some constant over log n. Okay. So superlinear lower bound. From the other side, the upper bound, Erdős conjecture that the maximum cannot be much more than linear. So this is a major conjecture. Erdős conjecture that maximal is number of pairs is n to the 1 plus little o1. And so far, we can get the upper bound of n to the 3 half, again, by Turan's theorem. Let's do that. So easy bound is n to the 3 half. How do we do that? Well, proof. We have endpoints. You build auxiliary graph gamma, where the vertex sets are the points, and the edge sets, if only 2 points form an edge, if their distance is of unit distance apart. Okay? And the key observation is that gamma is K2-3 free. What does K2-3 means? Let's see why this is true. This is basically two spheres can only intersect at 2 points. Two cycles in the plane can only intersect at 2 points. So suppose you have a K2-3. You have X and Y, right? Okay, maybe let me use U and V. Look at how large of a K2T can be. How large can T be? The common neighborhood U is here in this graph gamma. That means the neighborhood of U must be here, right? And the neighborhood of and V is somewhere here. Neighborhood of V must be of radius 1. Right? This is radius 1. And it can only intersect at 2 points. So K2-3 free. This implies, well, the number of edges of gamma is precisely the number of unit distance pair, right? That's by definition, which is at most the extremal number of n, K2-3, which we know by Kohlrausch-Turan is big O of n to the 3 half. Easy. The bound that we're going to prove is n to the 4/3, improving this trivial bound. This was first proved by Spencer, Samarity, and Trotter, and Sekei gave a shorter proof. So theorem. Spencer, Samarity, Trotter, 84. Shorter proof is this proof. There are, for any endpoints in the plane, there are at most 10 n to the 4/3 unit distance pairs. Okay. How do we prove that? Using crossing lemma. So how can we make use of crossing lemma? We're going to build a different auxiliary graph than here. Still, the vertex sets are the point sets, but the edges are not determined by unit distance pairs. What we're going to do is now, okay, we're going to build the auxiliary graph gamma, where still vertex sets are all the endpoints. For each point, which is each vertex, V, we're going to draw For each vertex V, we're going to draw a unit circle around it. Okay. Maybe I should do some cleaning first. So let me do some cleaning first. I have lots of space here. Very good. Let me do some cleaning. Let me delete this for now. Proof. We have these endpoints, right? Now we can so what we can do is we may assume that every point is involved in at least two unit distance pairs. By moving points if necessary. Okay, what do I mean by this? So suppose you have some points. So these are unit distance, right? And you have a point here, very far from the others. It's not involving any unit distance pair. You just move it closer. You move it here, so it's maybe involving one, right? This can only increase the number of unit distance pair. That's in the direction that's good for us. We want to upper bound it. So if you increase it, we can still upper bound it afterwards. That's good. But I also assume it's involving at least two. At least two means, so again, this is 1, 1, 1, right? Now, if you have a guy that look like this guy is only involving just one, then you just move it here, move it to this position, so involving two. You can always do that, all right? So every point now is involving at least two unit distance pairs. We build an auxiliary graph gamma, where the vertex set of gamma is the set of endpoints after we moved it, if necessary, as to have this property. What are the edges? Let's first draw a point V in P. Draw a unit circle around V. What do we know? We know by this assumption that there are at least 2 points on this unit circle because every point is involving at least 2. So this implies on the unit circle circle around each V in P, there are at least 2 vertices. Okay, so you have at least 2. So maybe in this case, I have 3. If you have 3, so what are the edges? We're going to draw edges. This is the edges. One edge, you just draw a cycle. They induce a cycle of length. If there are T vertices, you draw a T cycle where consecutive points along this circle form an edge. Now, what we do is you put an edge between every 2 consecutive vertices. on the circle. We do that for every unit circle around every vertex. This might give us, well, first of all, what's the number of vertices and number of edges of gamma? Well, vertices is n, we have n points. Number of edges is, let's say we have an arrangement. I forgot to say. Let's start with n points with maximum number of unit distance pairs. And let's assume the maximum number of unit distance pair, the number of pairs is m. M is bad. R is pairs. Yeah, R, why not? R, okay. What do I want to say? Okay. Then, if the number of unit distance pair is R, look, you have a unit distance pair here. Okay. From each point of view, I want to claim is the number of edges is 2R. That's what I want to claim. How do I explain that? Okay, this is how you can think of it. You can think of a unit distance pair, think of another directed graph D, where you put directed edge in both directions between a unit distance pair. Okay? So for a unit distance pair, you have two edges, this direction, that direction. Now, in terms of this direction, this is which correspond to the circle center at V. For this direction, all these edges, if you have three edges pointing outwards, you have three arcs in my auxiliary graph gamma, right? If you have four, let's say if you have five, then you have five edges. 1, 2, 3, 4, 5. This is in the direction V to W. Now, in the direction of W, you do the same. In the direction of W to V, you also have the same thing. So every unit distance pair is counted twice. Okay? You here require some explanation. Try to write it down. Every unit distance pair counted twice. Okay. The one thing we should note is that this is a multigraph. Could be a multigraph. There's no loop, but the edge could have multiplicity. Each edge has multiplicity at most 4. Why is that true? So the worst case is you have V, right? There are only 2 points. V is only involved in 2 unit distance, so 2 points on a unit circle. You have an edge here, multiplicity 1. You have an edge here, multiplicity 2, right? But then these 2 points are on the unit circle of another point, U. Then you have an edge here and the edge here. 3, 4. So every edge could have a multiplicity at most 4. This is the maximum case. That means delete the multiple edges, we will obtain, make it a simple graph. We get gamma prime. You have n vertices, and E of gamma prime is at least R over 2, right? Number of edges divided by 4. So at least R over 2. Now use crossing lemma. The number of crossings of gamma prime on one hand, crossing lemma implies that this is at least the number of edges cube over 100, the number of vertices. So this is R cube over 800 n squared. Okay, that's the number of crossings in gamma prime. On the other hand, when do we have crossing? Well, whenever you have crossing is only caused by two circles, right? These are the edges. Maybe that's not a good picture. Here's a better picture. So if you have vertices here, 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 you have an edge here, right? And on this side, you have vertices. Oops. Vertices here. Let's say here, here. Then you will have a crossing here. Okay. You have a crossing. And most two. There's another one here. And another one here. So all crossings occurs at pairs of unit circles. And every pair of unit circle contribute to at most two crossings. Each pair contributes at most two crossings. This implies crossing number of gamma prime is not crossing number of crossings in this particular drawing is at most 2 times the number of circles. And the number of cycles is what? Pairs of cycles. And we have n circles, n choose 2. So putting these two together, we have the desired bound. Okay. Any question? I go a little bit over time. So if there's no question, we're gonna pick up from here next Tuesday. Thanks for listening.